speaker is Julio Campario, talking about the evaluation of black soldier fly larvae as feed additive through cell-mounted SHK1 cell lines, polyphenol accumulation, antioxidant response, and cellular proliferation.
Thank you. Thank you everyone for being here today. Well, my name is Julio Camperio, PhD student at the University of Miami with Dr. Benetti and Dr. Jorge Suarez. I'm not going to read the title again. It's very wordy, so we'll get right into it. I want to first bring your attention to this publication that we published 2 or 3 weeks ago that covers part of what I'm going to be presenting today, which is the effect of different feed types on the black soldier fly, growth parameters, nutrient accumulation, but more importantly, the bioactive polyphenol accumulation in the larvae, and I'll be talking about that in the presentation. But it's a lot of information to cover, so if you're interested, I think you can scan that QR code and I'll bring you over. So to kind of give a brief overview on the black soldier fly meal industry, I would say, it's been traditionally seen as a fish meal or soybean replacement. It's a protein ingredient. It's in fact sustainable. These larvae can eat pretty much any organic waste you give them. We've seen even salmon aquaculture waste sludge. They'll eat that, no problem. It is a natural ingredient that gets produced. And at the end of the day, it does create a good story, whether you're producing feed or you're feeding your fish with this ingredient. It always sells a good story. But when you really start to look at it, we're noticing that there's 3 main challenges or issues within the industry, with this ingredient, I would say. First one is the nutritional profile. When you start to really compare the amino acid and fatty acid profile of black soldier fly meal with fish meal or soybean meal, it doesn't really compare as much. So it's kind of hard to compare this ingredient with the other protein ingredients that we're trying to replace. The second one is it's an issue of volume production. Even though there's multiple companies around the world, there's multiple companies around the world that are producing black soldier fly meal. When you look at the global volume production of fish meal or soybean meal versus black soldier fly meal, the volume differences are not really there. It is a new industry, so it has a long way to go to fully be able to become a main protein ingredient in aquaculture and other livestock. And then when you further go down the line, when you start to look at feed formulations at least cost with different softwares, you see that there's a big difference in the price. Fish meal can fluctuate, but the price is around 1,700 a ton. Insect meal is 3,000. So when you're formulating and you're trying to reduce costs, the software is going to have a hard time selecting this specific ingredient. Now I added here frass. Frass is the byproduct of the black soldier fly meal production process. It's traditionally been used as a agricultural fertilizer, but there's a handful of publications out there, and I think later today we'll hear more about it, on how it's being included in diets for omnivorous and herbivorous species. They tried it once with pompano. It didn't really work too well, but with catfish, tilapia, and shrimp, it seems to be working really well, and the price is really competitive. Obviously, there's a lot of regulatory frameworks to go through because it does contain excrements of the black soldier fly, so you're going to have a hard time selling it commercially. But that's just something to keep in mind. So with that said, we are aware that including black soldier fly meal in diets has positive effects, and we'll hear all about it today. But we're based on these challenges that we've identified, could we use insect meal more as a functional ingredient or as a feed additive? So what we did is we evaluated, the first part of the project was to evaluate the growth performance and feed efficiency of black soldier fly larvae when fed different types of organic waste produced commercially in the Miami area. And then we utilized cell models, SHK1 cell lines, to evaluate these different batches of black soldier fly in terms of cellular proliferation and antioxidant capacity. So what we did, we partnered with different producers in the Miami area to collect organic waste produced commercially. We have kitchen waste made of tomatoes and lettuce, agricultural waste, dragon fruit, malanga, boniata, and yucca, aquaculture sludge from Atlantic sapphire, aquaculture offal, again from Atlantic sapphire, and then a 5th treatment, which was a mix of all these 4 treatments together. And these were essentially the feed for the larvae. So we essentially set up a small black soldier fly rearing unit, I would say, It was temperature and humidity controlled. Our experiment, as you can see, we had 5 dietary treatments, 4 replicates. We basically stocked 200 larvae per container or per replicate. And every 3 days, we fed the larvae, replaced the substrate, and then took a biomass count. And the trial lasted for 15 days. Again, I'm not going to get too much into all of this because I want to get to the grain of the presentation, which is the cell lines. But we see that with diets that are more nutrient dense, like the mix and the offal, we had a significantly higher biomass gain versus low nutrient diets like the kitchen and the agricultural waste. Same thing with FCR, very similar pattern. High density is more efficient in terms of FCR. Biomass was similar to the graph I showed before. Survival was pretty amazing. Even the larvae that consumed aquaculture sludge, we had across the board more than 93%. And then when we look at dry matter, so the nutrients within the larvae, again, we see high density diets produced a higher density black soldier fly larvae. This is just to show you the difference in size between the treatments, quite drastic. And then here a picture to show the difference compared to a coin. Then we go into the cell lines. The way cell lines work is, I like to describe it a little bit like rotifers or teammate. You have a culture. In this case, it's a sterile environment. You give them nutrients, they grow. Once they reach a certain density, then you can seed them in a 96 well plate. You expose them to whatever treatment you're looking at. And then with a microplate reader, you first colorize the wells, and then with a microplate reader, you can analyze those results. These are just some pictures that we've taken through our cell lines at our lab, SHK1, which is the head kidney, and then RT gut, which is rainbow trout intestinal cells. But for this project, we just use the SHK1. So now going into the results, when we first look at proliferation, so we see here, we have the control, so no compound added. BFS is the positive control, bovine fetal serum. And then all of our treatments here of the black soldier fly were included at 1.4% inclusion. And these results are 5 days of culture once the treatment was added. So we see that across the board, we have growth from all the different treatments. But when you look at the difference, we see that in this case, the larvae that consumed plant-based waste had a significantly higher proliferation than the larvae that consumed animal waste. So in this case, it was aquaculture, offal, and sludge over here. So we're starting to kind of see a pattern. Then we move into cellular antioxidation. Again, we have a control here with no compound added. Negative control is 0.1 millimolars of hydrogen peroxide, which causes an LC50. We have our positive control, vitamin C. In this case, it was, if I'm not mistaken, DSM, vitamin C at 250 ppm. And then again, we included our same treatments at 1.4 inclusion. And again, as we saw with the previous slide, we saw that larvae that consumed anything that was vegetable waste had very similar antioxidant response to vitamin C, versus larvae that consumed, again, animal waste had results very similar to the peroxide. So what seems to be happening is that the insect meal fed with vegetable waste has both antioxidant capacity and it promotes growth. And what seems to be going on is vegetables and fruits, that's why they say an apple a day keeps the doctor away. These kind of food sources contain polyphenols, which are antioxidants. And so what we're seeing is that the antioxidants that are within these fruits and vegetables are going from the substrate all the way to the larvae, and is having positive effects on cellular antioxidation. So the next step we did, we took the same samples and we used the Follin method. The Follin method was originally developed to quantify total polyphenol concentrations in red wine. And it's still the standard method to quantify TPCs in the food science. And again, we see, as we keep on going through, that the vegetable-based black soldier fly meal had significantly higher total polyphenol concentrations than the larvae that consumed animal waste. Now, something interesting to note is that the mixed treatment contained 50% animal waste and 50% plant-based. And these two, the kitchen waste and the agricultural, were 100% vegetable waste, yet they statistically had very similar results. So what seems to be happening, and this is something that we have to further evaluate with a dose response of total polyphenols in the feed, is that the larvae have reached a maximum accumulation of TPC within their tissue. And it's possible that above this value, it physiologically wouldn't be possible for them to accumulate more. But again, to look more into that, we would have to do a new treatment with greater levels of TPC in the diets. So to wrap it all up, at we standardized the BSFL reading process and protocol for consistent and repeatable results. We've done these results were the final results of our 4th trial. So we produced 3 different batches of black soldier fly under consistent results, and kind of were able to predict what was going to happen. We were able to establish a cell lines lab, where at the moment we have immortalized SHK1 cell lines, which we plan on to use to evaluate further additives and ingredients. BSFL, black soldier fly, are in fact vectors that bioaccumulate desirable nutrients provided that I feed. This has been shown in many publications. Depending on what you feed the larvae, most of those nutrients will accumulate in their tissue, but there's always a limit by which those nutrients will absorb, especially if you look at long-chain polysaturated acids, PHAs, EPAs, they will accumulate, but there's always going to be a certain limit. And for us, what we were mainly interested in is, well, they are in fact accumulating antioxidants and polyphenols in their tissue, and that's what we're trying to see more as a functional feed ingredient rather than a whole protein ingredient. So with that, I'd like to thank all the partners that helped us, especially the Florida Aquaculture Review Council. They were the ones that funded the majority of this project, and I think if you scan this, we can connect further down the line if there's any further questions or future collaborations. Thank you.